Okay, good morning. I'm going to explain to you immediate settlement on a cohesionless soil. Cohesionless soil is like a granular soil. Example of this one could be sand or gravel. So in this calculation or this analysis, I'm going to specifically discuss to you the Meyerhoff's method and the Burr and Martin's method. The next one is we have Smartman's method, but for now I'm going to focus on Meyerhoff's method. So in this method, you are going to consider this formula that you have this pressure. Okay, wait. And then settlement, I should say, and then you have the net foundation pressure increase, the width of the footing. Let's say if you have footing here like 1.5 by 1 point, or let's say 1.5 by 1. Width is always the smallest value of your footing, and you have here over 2 and CR. What is CR? As you see here, it is these methods that you can have the relationship between CR and N. N is the number of blows that could be taken from the SPT test. That is the number of blows at the last 300 millimeter. All right. So both methods consider the soil beneath the foundation and the surface layer. So there are a lot of layers underneath of the footing. But take note that these De Beer methods and taking consideration on the depth beneath the footing, your layers should take consideration of your depth that should be 2B to 4B. That is, for example, if this is your foundation, this depth of layers that you will have should be from 2B going to ranges from 2B to 4B. For example, if your B here is 1 meter, then 2B is like your depth should be 2 meters to 4 meters. Alright? Okay, so formulas that you are going to use here, you have the CS, constant compressibility, is equal to CR, and then effective overburden pressure at the point tested. Usually this is in the center of the layer. And then you have the immediate settlement here, no, which is H over CS. I've already introduced to you the CS above. And then this is the effective overburden pressure. This is the vertical stress at the center of the layer. And yeah, the same with the effective could be like equal. Okay, depending on the depth at which CR was measured. Alright, for example, you have your foundation 1.5 meters square. So the footing is square. This one. And then the pressure is 300 kilopascal. Then founded at the depth of 0.75, meaning the bottom of the footing is 0.75 meter from the ground on a granular soil. So since we're discussing a cohesionless type of soil, so this corresponds to granular soil. The soil may be regarded as saturated throughout. The unit weight is 20 kilonewton per cubic meter, and the approximate N to Z value is given to here, meaning during the SPT, the first 1.75 meter has N equal to 12, and then N is equal to 16 for the succeeding layer, and the remaining layer is 24. In other words, that this one is strongest. Okay, the more number of blows that you have, the more stronger is your soil. Okay, so the water level is 1.5, okay, below the surface of the soil. So in other words, if you have like this footing, according to this is 0.75 according to this problem, 1.5 is here, right, is your groundwater table. Okay, right. So take note, as I said, that your depth should be 2B to 4B. If you have 2B, B is 1.5, that is 3 meters, and then 4B is like 6 meters. So the total depth of your consideration from below the footing should be like maximum of 6 meters. That is from 3 meters going to 6 meters. Alright, so let's check this layer. As we said earlier, 0.75 is here, okay? And then from this NZ relationship, you have the N values. You have N is equal to 12 at a depth of 1.75 meters. At a depth of 2.75 meters, so this one is 1, you have n is equal to 16. From 2.75 to 4.25 is also 24 and 24. We decided like a layer of 1.5 meter here and 1.5 meter also here for the fourth layer. Alright, so it's up to your decision as long as it ranges. Is the D should be from 2B to 4B. Alright, now as we say, groundwater table is 1.5 meter from here, okay, from the ground. So the water is present here, okay, 1.5 meter. Alright, now the layer center at every, the depth of every center of the layer. So if this is like, if this is 1 meter here, it follows that the center is 0.5 here, okay. Going to here is also 1 meter, so this becomes the center of this layer too. 1.25 plus 1 is 2.25. And then you have here, this is like 0.5, and then this one is 0.75, so that makes a difference of, or a total of 1.25. 2.25 plus 1.25 is 3.5. In other words, you just have to measure every center of this layer, okay, because we need it for this effective overburden pressure. Alright, so first you have already identified the thickness, and then out of it you get the formula for CR400N. As we say, the first layer is 12, second layer 16, and then you have 24. So you have 12, 16, and 24. Just multiply, you have 4,800 Newton, or it could also be the same as 4.8 kilonewton. Okay. Now, PU1, okay, or the what's PU1 again? I'll repeat it. It's effective overburden pressure at the point tested. We are testing at the middle. Okay, this is the middle. If you are going to look back, this is the middle or center of layer. Take note that for the first layer, at this point, there is no water table. That is why you have the unit weight of the saturated water 20 times 1.25. Where can we get 1.25? Here to here is 1.25. We already measured it earlier. Alright, so that's 1.25. Now, second layer here, at the center of the layer has already water. Its distance from above is 2.25, but its distance from the groundwater table has to be identified. Okay, so it is just like here, from here it is just like 2.25 minus 1.5, right? Because 1.5 is over here. Here is 2.25. That means your water presence is just has a depth of 0.75. Okay, so 20 times 2.25 versus 2.25 here. 2.25 is coming from here. Going here is 2.25. But the water going here to the center of this layer is just 0.75. The next, from here going here to the center, like 3.5 minus 1.5, you have 2. And then again, from here going to the center here, at the last layer, 5 minus 1.5, see? It becomes 3.5. In other words, you just have to multiply the unit weight of the soil to its total distance, which is here, total distance like 2.75, and then I don't know this one. Okay, 2.25 at the center, 3.515, and then subtract it with the presence of the water. Alright, so once you have P, the effective overburden pressure, then you can compute CS, because C is just like 1.5 times CR over the effective overburden pressure. That is at the center of the layer. CR is already here, and then this PU1 is already here correspondingly. So you get the value of CS. Alright, the next we need to get this stress. What's the stress? This is a vertical stress increase. The increase of the stress at the center of the layer of the thick, okay, of the layer. So how are we going to calculate this one? We use the Fathom chart. This is the Fathom chart. Now in the Fathom chart, as we discussed before, you have here the N and then the M factor for us to get this influence factor. N is equal to B over Z. Z is the depth, okay, while M is equal to N M is L over Z. L in this side, B is in this side. In this case, B and L are the same. So it's the same 0.75. And then Z here is 0.5. This one is Z, okay? At the center, which is 0.5, okay? At the center of the layer, these are the center of the layer coming from the bottom of, okay, the footing, 0.5, okay? So that's why you have 0.5 and then 1.5. So it's just like here, footing, the first layer, you have here 0.5, okay? Second layer is this layer 2, layer 1 is 1.5, right? It's here. And then how about this one? 1.5 and 1 plus 1.25, that becomes 2.75, and so on, 4.25. These are the center of the layer coming from here, from the bottom of the footing. Now, once you have this Z and B and L are the same, so you get this M and N. So if this is 1.5, for example, this is 1.5, this, and then 1.5 is over here. Okay, you go over there in the middle, so your value is like 0.213. You do the same for layer 2, layer 3, layer 4. We have similar calculation of this in the previous one, in the previous discussion. But let me show you again. For example, 0.5. If your 0.5 is over here, this is 0.5, and then 0.5 is also here. So if you're going to follow this one over there, this is 0.5. This is between 0.09 and 0.08. That's why your answer here is 0.088. Okay, and then multiply it by 4 because we have 4 equal areas. Take note that we consider the immediate settlement at using fathom chart at corner of the rectangular square. So this is also corner of this area, similarly here and here. So we just multiply it by 4. Now, in the case if you have different section or areas, then you just have to add all the immediate settlements that you can get at every corner. So, now, the stress at the increase at every layer, just have, okay, multiply by the stress P, net pressure, which is here, 300. Net pressure, if you have here, is the pressure here, okay? The unit weight is like 300. The given pressure is 300, and then you deduct it by 0.75, which is the depth. Okay, the depth from the ground. The depth from the ground here, going here, is 0.75. Okay, the unit weight is 20. That becomes you have 285. So you have here 285 times 0.852, which is here. Here, 285 times 0.352. 285 here times 1.12. 285 here times 0.06. So this gives you the value of this stress, increasing stress at every layers. Now, once you have this increasing stress at every layers, you have here, and then you have this formula PO, which we have calculated earlier. This one, you have, for example, for this one, you have natural logarithm of like 25 over the same PO. You have 25 plus, what is this increasing stress at every layer? So for example, here is 243. So you can get this 2.3721. Similarly, you have also in the same formula, you can calculate this one here and here as well. So now the final settlement, this is the settlement at every layer. The first layer has settlement of 0.00824. How do you calculate it? H over CS. H is the here, the thickness. Okay, thickness of layer 1 is 1, 1.5, and 1.5 for 3 and 4. CS here, where CS, this is CS, has a value which we have calculated in the previous slide, is 288. So this one is like 1 over 288 multiplied by A at that layer, which is this one, 2.3721. We have this value. This is the immediate settlement at layer 1. This is for layer 2, layer 3, and layer 4. If you are going to add all of them, this becomes the total immediate settlement beneath the footing of this footing for this particular layer at a depth of, what's the total depth? It's around 5.75 meters. Okay, so this is just the location. No, this is just the settlement at one footing. Now, if you are going to take or calculate also the settlement of other footings for you to check if you have like common value of your settlement of or regular settlement, then you are going to analyze all the footings that you have in your building structure. So that's all for the beer methods. We'll have the smart man's method in the next video. Thank you.